Swayam Prabha. Digital India. Educated India.
Previously, we discussed pretty fast about alternating water column, about PTO, and I didn't discuss too detail about how to design PTO. Basically, give you a principle. So before that, I move to new topic. I want to give some chance to hear your questions. Then we discuss a little bit before we talk about power electronics side. Okay, and why we first let us say why we have accumulator for energy storage. What are the reasons? You want to stabilize the pressure, right? So that way the wave the very irregular like that. Where your generator, you don't want generator like that. Therefore, you put an accumulator here, then you can maintain the generator during the operation constant speed, right? And some design, for the design, let me say that way, you need to choose accumulator large enough so that you can maintain this constant speed. You need to consider wave period, wave situation, right? So it's important. Some of the design, the accumulator energy first, reach a certain period of time, then turn the generator on. After generator rotated, when it's fully discharged, then everything turn off. Right. So it doesn't need to be continuous operation. Some designs not make the certain not continuous operation. The reason is they want to have the generator operate at the maximum efficiency range. Right. Okay. This figure, there's energy there also. And let's take a look again. And before that, I want to Google to say I didn't put the figure of Benke. Okay, this is Benke turbine. Okay, give you sense what it look like. Okay, and let's imagine. Actually, it's self-adjusted cross-flow turbine. Okay, so let us say that way. So look at this figure again. I make it slightly larger. Okay, this direction is flow. This direction head, right? How high this water drop? Okay, and water head time flow was that power. So this is why there's this line, 10 megawatts, right? This is 1 kilowatts, and that is 10 kilowatts, right? This is 1 megawatts line, right? Basically, for cross-flow turbine and Benke turbine, okay, and the work with for low head, right? 3 meters to 200 meters at the flow rate. So this is 0.2 meter per cubic meter per second to about 8, right? So at the power rated less than 1 megawatts, right? It can be 100 kilowatts. So for this suggested range, energy and head relationship, energy head relationship there between there's a flow rate. Head time flow rate will be energy. What this is why this figure there's also energy here. Is this clear? You try to say what the head and relation energy, right? So this head time flow rate will be energy. Head and flow rate, that is the way to the guide to help simulate the turbine. Overhead is just potential energy. This is overtopping. Overtopping, you accumulated water there, and the energy is just delta H time. This how much mass go down at what kind of rate. Is this clear? Right. So anyway, so this figure shows that how to choose a turbine, right? And basically, this is very popular for the traditional hydropower, right? That is for the very high mountain area, you go down, right? And this is for mostly overtopping. The head wouldn't be that high, right? Okay, and just cross flow and the type of turbine. Okay, and self-rectified turbine, self-rectified generator, I think is very interesting, right? Or as you say, your system, you don't want to have generator in the direction. There are many ways to achieve that, right? The check valve, they use piston, bidirectional motion, use check valve to convert bidirectional motion into fluid motion into unidirection, right? And the West turbine is self-rectified, right? It's nice, and air in and air out, the generator always rotates one direction, right? But it's still, there's another media, intermediate, you use water drive the air, right? So then air drives this self-rectifier West turbine or impulse turbine. Here, and this fluid direct drive that is more direct. When you can do at different stage, right? And you can, the best is the fluid side direct convert bidirectional motion into unidirection. Another mechanic side, including check valve, one-way clutch, right? All this will be in this mechanic motion side. And sure, you can achieve something in electric domain, right? The generator, if you go that way, and you have voltage like this one, you convert into AC to DC. Okay, so but this design side, so far, there are not. There's some research going on, but it's not that popular in the industry side. And for example, this design looks interesting. I didn't look into that. I don't know why the student, after graduate, they didn't write a paper. And his advisor is Professor N.S. Locum, is my advisor's advisor. So, and I like the design. I had some communication with her, and I don't know what's the problem here, right? She created a website, put it there, but no company follow up. There must be some issue, right? Or efficiency, whatever like that. And I didn't look into that. If you have interest, you can look into that. Do some simulation. It's not that hard. So I have to say, a lot of figures I put here at the beginning, I said, and I didn't get a chance to look into that for education purpose. Previous 3 years when I teach that, okay, I tell students don't put it in public domain, just for education purpose. But I didn't get a chance to put the reference and where I learned that might be in public domain. Okay, anyway, so there are many different type of design of PTO, and PTO side, and we talk about the mechanic system, electromagnetic system that can be scaled up, scaled down in large range. In my view, such kind of system can work in 10 watts to I would say 10 watts to 500 or 100, 500 kilowatts level. You want to build some system like 1 watt or 0.1 watt, definitely the system wouldn't work right that way because the friction, right, that give you some sense, right? And such kind of system design is very tricky, and you need a lot of know-how. I give you one example like that, okay. And ball screw, and the ball screw, this angle to have lead angle, right? If lead angle is large, the motion transmission would be small. Basically, you move up and down, the generator rotates at lower speed, right? However, if your lead screw is too small, the generator speed is high, but the ball screw's transmission efficiency is not good, right? Sometimes, okay, you may find, wow, I need to use larger needle ball screw, and I put another gearbox, 1, 2, 3, whatever like that. Certain efficiency will be better, right? So, and in this design side, you have mechanical system. You need to care about alignment. On auto design like that, for example, you have generator, you have ball screw. In between, probably you don't have rigid coupling, you don't have flexible coupling to allow misalignment, because you put two shafts together, there's no way these two shafts will be perfectly aligned. So you need to have some flexible coupling, right? So another thing in this system, you may think you have preload and backlash this system. And for example, here, the rack pinion, easily you have backlash, right? So you may have some preload. When you have preload, if preload too large, then you have larger friction. So, and this is all kind of trade-off. When you design that, for example, the bearing look like here, and how to compensate the thermal expansion loss, right? Bearing, the support, you have usually two ends of bearing, right? If this shaft become thermal expansion become longer, how to allow this bearing to move up and down? Therefore, such kind of bearing usually you have fixed constraint here, allow another end, and that is a slide, right? And such kind of idea of design, and you can look into Professor Alex Slocum's open courseware at MIT, fundamental design. So they teach you a lot of such kind of know-how. When I was student, my advisor gave my advisor is Slocum student Samuel Nafee, and Professor Samuel Nafee gave me Professor Alex Slocum's book. Let me read. In that time, I don't have experience in the design. I read the book. Wow, I fall into sleep like that. Okay, and after I working years in company, I look into the book again. I feel, wow, Slocum really has not a good experience in the design, right? It's different. So I always tell students the design is not so easy, right? It's not something, okay, I get technician, I can get the work done. No, it's not like that, right? So a lot of know-how or a lot of knowledge, right? Another popular mistake our group face when we come to energy converter design is a set screw. Set screw can be nightmare. You have shaft like that, you have coupling. Okay, I use set screw here, it's easy. The real life, you set screw, wow, at the beginning of the work, you test, everything get loose, right? So you need to have such kind of experience. And design is like a swim, okay? It's not something like that. You say someone swim. No, I know how to swim. You jump into the water, right? you will sink down. Right? Design, you need to make some mistake and learn through the process. Okay, so I wish I have a chance to teach you guys a little bit thing about the design side. And when I teach a course at Michigan, at Virginia Tech, I use Professor Ernest Slocum's fundamental design. You search that, you learn how to design the system. Again, if you didn't have experience, then you look into that. You didn't get a sense. Okay, after experience, you look into it, then you will find you learn more. Okay, so keep on practice. This is without in practice, and just look at other people's swim, you wouldn't learn. Okay, so this design side. So anyway, and this different different PTO, they have different working case, right? And hydronic system, I said you want to have 100 watts design would be pretty bad, right? Probably, I would, from my own experience, I probably think hydronic system would be good for kilowatts level and above, right? Kilowatts, 100 kilowatts, right? Even more. Okay. So, and where's turbine? There's an advantage because you feel large shock, and then this air already dumped out, right? So this system, why this system has been used for decades to build 500 kilowatts, 400 kilowatts system in European country, in Japan, right? Like that. So this system can also work on small scale, like 10 watts system, and people will use that to build navigation mark. Okay, so there's some problem here. Some problem you can imagine that way. The air is very dirty, and when I visit the Spain company and they build this wind turbine like that, and they have some sort of the spray water on the turbine to clean the salt, right? In the ocean, right? Then there's some moisture, take some salt, and they accumulate salt. They have to spray water to clean that. So the efficiency here, overall, to where efficiency, what mean consider the energy. You just imagine that we take. Let me take back to this figure. Okay, I give you some comments. Okay, so and you go here, right? A lot of energy get reflect back, right? And some energy go to accumulate the air chamber. Air chamber, the energy drive the turbine, right? I say the turbine efficiency can be 50, 40, or 70% from here, but there's energy loss through certain energy loss here, right? Overall, such kind of efficiency, will to where efficiency is not that high. Okay, some report shows 40%. Mostly is much smaller than that. Okay, so by the way, and this turbine is their Betz limit or not? You know what the Betz limit? Betz limit is wind turbine, right? And it's 59%. You can, is wind turbine like that, it cannot be 59%. You guys care about the Betz limit or not? Who raise hand? Yes? Okay. And okay, can you explain what's Betz limit?
When the wind turbine is converting the wind power into electricity, it would the maximum amount of wind power which could be converted back is determined by the length limit.
Okay.
So for the wind turbines, it is 59%.
Okay, why is there such kind of limit?
A momentum theory, sir.
Okay.
And if we take the optimum value, that d by dx, find the critical point at that value.
Okay, so let me say that way. I will chat with Professor Samet. If he wouldn't cover that, I will cover some part next to the nature. Okay. Okay, so this is wind turbine, and they have look at this figure, right? And this ideal efficiency cannot be 50%, and also depend. I like this figure. Okay, depend on different turbine, then you have different efficiency limit, right? This turbine, take a look at here. I make it another. Okay. So you have popular 3-blade turbine, right? You can have 2 blades, and you can have 1-blade turbine, and you can have American turbine like that. You have Dutch turbine, and this turbine, they have different efficiency line. This is efficiency. This is tip speed ratio. Tip speed ratio is tip rotation speed divided by wind speed, right? So then it can have 59% efficiency limit. So the reason is like that. When the wind blow the turbine, and this nice figure. Okay, and this is streamline shape. Basically, when come here, hit the turbine, the streamline go outside become larger, wider, right? So then you have wind speed. Wind speed goes through here, decrease, right? It didn't decrease 0, but it decreased, right? So in such a kind of case, and if you consider wind speed decrease and flow rate pressure like that, you can find how large the wind speed decrease will be related with the power output, right? And if wind speed decrease at this moment by 1/3, in such a kind of case, you maximize the power output. Okay, therefore, you just imagine that way. You wind here totally blocked, the wind speed becomes 0, right? Then there's no energy get out, right? If wind speed there's no decrease, then there's no efficiency either. So for this reason, Betz limit is a scientific number you can get from the closed form solution, right? And you write a power as the speed of this go through here. You'll find you reduce by 1/3, you have best efficiency. Okay, so can the turbine efficiency more than 59%? Yes or no? Yes? Why? Oh, single turbine. Can we get more than 59?
Yes, sir. If we place the ducts, we can.
Yes. So you think that way, and the 59%, that is the flow line shape like that. And what if I put a wall or duct, right? Then the flow line we don't have such kind of constraint. Then we don't have such kind of maximum speed, maximum power as a function of the speed. Okay, so this is Betz limit. Okay, so keep in mind this figure shows efficiency. One figure is not that popular here. What's another figure? Is torque. Starting the torque and the speed. So for example, and this turbine, American turbine, the efficiency is not high. However, this turbine, the starting torque can be high. Starting torque, like if you work in very slow speed situation, starting torque is important because of friction, and you although you have to during the rotation, the efficiency is high, but you have to overcome the friction, right? For this turbine, you get sense. It makes sense to you. You say no, another blade, then another blade. This you have any places almost blocked, right? Then they try to generate more torque, right? Then the starting torque is high. Where this type of turbine, like, okay, most of the area is not covered, the fluid goes through, right? Before it rotate, look like nothing, block the water. Therefore, at the beginning, the starting torque will be low. Then you have high rotation speed, then you can generate high power. Okay. So when you choose a turbine, a lot of people, oh, efficiency is best, but you find a very slow water speed, and this can be even better. Okay, because starting torque. Okay, and I will try to say we can briefly mention that. I stop here, and I come back to lecture. Okay, so or and we say the advantage of different type of PTO and electromagnetic in large power range and hydronic and high power will be better. Pneumatic, there's an advantage, and however this type of thing, if water get into the system, is also horrible, right? In storm condition, you have multiple design. For example, some people they say, oh, gate, I close it. After I close it, I have side wind to let the air get out, right? In that way, they prevent the water get into the design. and overtopping device, and for the two will be very small generator and energy power milliwatts or watts level for tribal electricity and piezoelectric. Okay, so this is piezoelectric then. This is some emerging technology I think is fun and need to do more scientific research on that. Okay, so the PTO design and also structural design sometimes always couple together, right? So anyway, this hybrid design, there are many hybrid designs. This is just the one simple figure in literature. There are quite a few good review articles about a combined wave energy converter and wind energy. So let us continue talk.